All right, hello class. So today we're going to look at bivariate regressions. This is our introduction to regressions. This week is bivariate regressions. Next week we're going to look at multiple regressions or multivariate regressions. So let's begin. So we've already talked about correlations and how we use that to understand the relationship between two variables. So remember, we look at the strength of the correlation coefficient, we look at the direction, and it helps us understand what's happening between those two variables. Well, with regressions, we also have a number that we're going to look at that helps us to predict what would happen to the dependent variable based on the number that we see in the independent variable line. So it's a numeric description of how both variables vary together and allows us to make predictions based on that numerical description. So the regression coefficient looks like this, and it's y hat equals b naught plus b1 times x. X is our independent variable. It's the value for that independent variable. So if female is our variable where female is 1 and male is 0, in that equation we would put 1 for female, or we would put 0 if we wanted to predict what the male would be. Y hat is the expected value for the dependent variable. So our dependent variable therefore is y, and then y hat is what we use as a term for the expected value. B naught and B1 are constants that result from the regression analysis. So the B naught, which we also know as the Y-intercept, is the expected value when when x equals 0. In other words, so this value b naught, or the y-intercept, is actually only meaningful when x can have a realistic value of 0. So for instance, if we were looking at the pay grade of a federal employee, and we're trying to use the pay grade to predict salary, our expected salary would be B naught plus B1 times grade. That's our equation for this relationship. And then we would start plugging in. Expected salary equals negative 5132, right, from what we see here under B. And then plus 4779, which is our B1. We see here beside grade. As you can see here, it's also beside grade in the equation. And then we multiply it by grade. And we do that in order to then determine what the expected salary would be at grade 0, at grade 1, at grade 2, and so forth. So looking at bullet point 1, we see that the y-intercept tells us that the expected salary for employees at grade 0, right, when we plug into this equation, we type 0 in here, and we would multiply this times 0, which means that's 0, right? And so what we have left of the equation is negative 5133. So the expected grade salary for an employee at grade 0 is a negative value, which essentially means that you are paying the government back, which obviously is not logical, but that's what I mean by this last bullet point here, telling us that the value is only meaningful when x can actually be 0, right? So for the federal pay grade, it actually starts at, I believe, 3, and so a pay grade of 0 therefore does not allow us to predict anything realistic. Okay? Okay, so the B1 regression coefficient is the expected difference or the expected change in your dependent variable for a 1-unit increase in your independent variable. So this B is telling us direction, and to some degree it's telling us about strength. And so let's take a look at it. We're going to look at this equation again. It's the same output here, right? So we've got our dependent variable as our expected salary. We've got our independent variable as grade. We've got the same y-intercept, the same B1, but now we're talking about B1. So we can, this is telling us two interpretations, and they convey the exact same thing. As the pay grade of a federal employee increases by 1, say we have a pay grade going from 10 to 11, 11 to 12, and so on. Each increase in pay grade increases your salary by $4,779. And to set a different way, for each 1 unit increase in pay grade, federal employees earn $4,779 more. And so looking further into the regression coefficient, we have two outputs here. The first one is the one that we've already seen. The second one, we're now looking at age as our independent variable, as we can see here. So as age increases by 1, right? So as you go from 10 to 11, 20 to 21, 35 to 36, right? As you increase your age by 1, employees earn $502 additional dollars. We can see that B1 is higher for pay grade, for pay grade than it is for age. So this means that expected salary increases more as grade rises by 1 than as age rises by 1. Okay? So to calculate y-hat is the expected value of the dependent variable. I've said it before, I like to say things over and over because this is the learning process. So just trying to drill it in there. So calculate y-hat, say for that very first equation, that very first output we looked at, we see it here, expected salary equals this, right? So we plug into the equation the values that we see for B0, our y-intercept, and for B1, okay? And then we plug into the equation the value that we want for our independent variable. In this case, it is grade, okay? And so when we plug into this equation a pay grade of 4, what does it tell us? It tells us that our expected salary at a pay grade of 4 is about $14,000. Our expected salary at a pay grade of 7, we can see once we plug this in and do the proper math, is $28,000. And then at a pay grade of 11, we see about $47,000. This is actually pretty low compared to what it might be the actual. This is old data too. So if the lowest pay grade possible is 3, what would the expected minimum salary be for a federal employee? How would we do that? We would just plug in the number 3, right? And so the lowest expected pay grade for a federal employee is about $9,000, which can't really buy you much of a living. So we do need to increase pay wages in this country. But that's another story. Okay, regressions and dummy variables. A dichotomous or a dummy variable has only 2 possible values, and it's typically 1 and 0, or it may be 1 and 2, but typically 1 and 0. When the independent variable is a dummy variable, the y-intercept now has meaning, right? Why? Because the independent variable can exist at 0. So if we see here, our variable here may be gender. We have 1 for male, 0 for female. 0 means something. And so our y-intercept here is the difference, as we can see here, the difference between the independent variable with value 1 and with value 0. So this y-intercept is telling us generically the change in y when x changes by 1 And less generic, the change in mean salary when gender variable changes from female, 0, to male, value of 1. And the best way to say this in layman's terms is the difference in mean salary between men and women is $12,777. Okay, specifically men make about that much more than females. Okay, so our Y-intercept here is 34,000. That's telling us that's what the 0 makes. So that's what females make. And then we add this 12,000 or about 13,000, and that's telling us what males make more than females. All right, so let's take a look at what that looks like in the equation now. So what is the Y-intercept here? Hopefully you said 34,000. And what is the mean salary for women? Well, it's 34,000 because at 0, that's what our Y-intercept is. Okay? So what is the mean salary for men? Well, we should just add that $12,777 to give us about 47,000. Dummy variables can be coded in either direction. This is really important because some people get kind of confused and say, well, what if we code it the other way? Well, let's code it the other way. Okay? And so in the first scenario, the code for male equals 1. In this scenario, we know because of coding nomenclature, coding standards, that female now equals 1 and male equals 0. Okay? And so even though we recoded it differently, we should technically get the same answers, right? So our Y-intercept in this case should be 47,000. And what is that 47,000 telling us? It should be telling us what the value is at 0. And what is our 0? Our 0, because this is called female, our 0 is male. So the mean salary for males is 47,000. Same answer, right? And then it's telling us this negative 13,000, right? Negative 12,700. That's telling us that females make that much less than males. So again, it's telling us that if we take this 47 and subtract it by the 12,700, that we should get 34,000, which is still the same answer. Different equation, right? It looks different from the first equation, but same results. All right, so that is really it for lecture 6. I'd love for you to open the practice exercise now and to give it a go, try it out, and we'll see you in lecture 7.